For a moment, just a moment, let everything fall away. The noise of your day, the weight of your worries, the scrolling and the rushing and the constant forward motion of modern life. Let it all go quiet. Hello and welcome to Infinite Science. Take a breath. Look up. Not at the ceiling above you, not at the sky framed by a window, but in your mind's eye. Look upward into the full, dark, breathtaking openness that stretches beyond everything you have ever touched, ever known, ever imagined. Look into the cosmos. This is not a place of fear. It is not a place of emptiness. It is, in the truest and most profound sense, home. The vast, ancient, luminous home in which our tiny world is cradled almost invisibly like a single grain of sand resting at the bottom of the deepest ocean. Today, we are going to travel together. Not in a rocket, not through the pages of a textbook, but through the quiet corridors of imagination, guided by everything science has revealed about the true scale of the universe we inhabit. We will begin right here, beneath your feet, on the surface of a spinning blue world. And then, step by step, section by section, we will move outward, through the clouds, past the moon, beyond the planets, across the galaxy, and into realms so vast that even the word vast begins to feel inadequate. There are no words that are truly adequate for what we are about to explore, but we will try, because trying is what we do. It is what makes us human. It is what makes us, in our small and wondrous way, something extraordinary in this extraordinary cosmos. So settle in, breathe, and let the journey begin. Imagine you are standing outside. It doesn't matter where exactly. A grassy hillside, a city rooftop, a quiet beach. You are standing still, but you are moving. Right now, beneath your feet, the Earth is spinning at roughly 1,600 kilometers per hour at the equator. You don't feel it, of course. The planet is so massive, so smooth in its rotation, that all you feel is stillness. The ground beneath you feels solid, permanent, vast. It is easy, it is natural to feel that the world is enormous. From one side of a continent to another, the distances are staggering. It takes hours to cross them by plane, days to cross them on foot. The Earth feels large. But now, close your eyes and try to do something almost impossibly difficult. Try to imagine the Earth from the outside. Try to see it as an object floating in space. From a distance of about 12,000 kilometers, the Earth fits within the frame of your eye. You can see the whole thing at once, a ball, blue and white and achingly beautiful, suspended in absolute darkness. No ground now, no horizon, just a sphere rotating slowly, smaller than your thumbnail held at arm's length. That sphere is everything. Every mountain, every ocean, every city, every forest, every human being who has ever lived. It is all there, compressed into that tiny, glowing marble. The Earth has a diameter of approximately 12,742 kilometers. That sounds large, but compared to the solar system, compared to the galaxy, compared to the universe, it is almost nothing. It is less than a whisper. It is a single brushstroke on a canvas that extends beyond our ability to comprehend. To put it in perspective, if you were to shrink the observable universe to the size of a basketball, the Earth would be so small that no microscope yet invented could find it. We are, in the cosmic sense, an infinitesimal speck. And yet, there is this thing about specks, about tiny, improbable places, that demands attention. Because this particular speck, this pale blue dot, is something astonishing. It is warm, it breathes, it is alive. Look at the atmosphere, that thin, gossamer shell of gas that wraps around our planet. If you were to scale the Earth down to the size of an apple, the atmosphere would be thinner than the apple's skin. Less than that, actually. It is a fragile veil, only 100 kilometers thick. And yet, it is everything. It keeps us warm, it gives us air. It shields us from the constant, lethal bombardment of cosmic radiation and solar particles that would otherwise strip life from the surface in geological moments. The biosphere, the thin zone of life on this planet, is even thinner. From the deepest trenches of the ocean to the highest peaks of the Himalayas, life occupies a layer perhaps 20 kilometers thick. A 20-kilometer slice on a planet 12,000 kilometers wide. That is 1.5 thousandths of the planet's diameter. If the Earth were a person, the biosphere would be the thinnest, most delicate layer of their skin. And within that sliver, within that skin-thin layer of breathable air and drinkable water and rich, dark soil, every human civilization has ever been born. Every empire and democracy and tribal council, every war and every peace, every poem and every song, every discovery, every love story. Every moment of beauty that any human eye has ever witnessed. It all happened here in this paper-thin layer on this tiny sphere. The continents, which seem so permanent and vast, are in fact geological accidents. The drifting remnants of an ancient supercontinent, still slowly moving, still slowly reshaping. The oceans, which cover 71% of the Earth's surface, are only about 11 kilometers deep at their deepest point. If you smoothed out the entire Earth to a perfect sphere, the water would form a layer only about 2.7 kilometers thick. Deep to us, of course. Impossibly, crushingly deep to any diver, but paper-thin on the scale of the planet. Stand on any mountaintop, look out at the curvature of the horizon if you are high enough and the air is clear enough. What you are seeing, that gentle curve, that suggestion of roundness, is the edge of your world. The boundary where your air ends and space begins is no further above you than a comfortable morning's drive down a highway. Space is close. It is always close. Right above you, somewhere between 60 and 100 kilometers up, the atmosphere becomes so thin that there is functionally nothing there at all. An astronaut in the International Space Station, orbiting 408 kilometers above the surface, can look down and see individual cities, mountain ranges, rivers. The detail of the world spread out below them like a living map. They are not far. Cosmically, they are barely off the ground. But even from that relatively modest vantage point, something shifts. Something in the human heart shifts. Astronaut after astronaut has described it. This feeling of profound perspective, of sudden, heart-stopping smallness and beauty. Looking down at the Earth from orbit, you see no borders. You see no countries, no divisions, no flags. You see only the whole. One world lit from one side by one star, swaddled in its thin breath of air. The Japanese call this shift, in perspective, the overview effect. It is the cognitive change that happens when you see the Earth from space for the first time. This overwhelming sense that we are one small thing, together on one small world. That what divides us is vastly outweighed by what connects us. We haven't all had the chance to go to space, but science gives us that perspective for free. Knowledge, true, deep, accurate knowledge of what the universe is and how big it is, delivers that same shift. The same quiet, humbling, wonder-inducing realization. We are small. The Earth is small. And that is not a tragedy. It is a miracle. Because in all the vast, cold, empty universe, in all the staggering trillions of kilometers of darkness and frozen gas and radiation, this one small place is warm. This one small place has rivers and clouds and the sound of rain. This one small place has birdsong and laughter and the smell of bread baking and the feeling of sunlight on your face. we begin, here on Earth, not because it is the center of anything, but because it is everything to us. It is our anchor, our origin, the world we will leave in our minds tonight as we journey outward, and the world we will return to, transformed at the end. Remember it as we go. That pale sphere of life in darkness, that fragile, beautiful thing. Because everything you will see from here, every planet and star and galaxy and supercluster and cosmic web, will in some way make that small blue world more precious, not less. When you understand just how much space there is and how little of it has what we have, then the miracle becomes clear. Then the weight of the gift becomes real. So take one last look at the home you know, the ground beneath your feet, the sky above your head, the smell of the air. And now, let us take the first step outward. The atmosphere above you is not simply air. It is a layered, dynamic, astonishing system. The troposphere, the layer in which all weather occurs, extends only about 12 kilometers above the surface. Above it is the stratosphere, where the ozone layer absorbs ultraviolet radiation from the sun, protecting the surface below. Above that, the mesosphere, where meteors burn up as they fall inward. Above that, the thermosphere, where the International Space Station orbits, where the aurora borealis shimmers on solar wind particles. And above that, the exosphere, the final, whisper-thin outpost of atmosphere, gradually merging into the vacuum of space with no clear boundary. The Earth is a system, not a simple object, but an interconnected living system of rock and water, and ice and air and life, all interacting continuously. The ocean circulates heat from the tropics to the poles. The forests regulate the composition of the atmosphere. The soil teems with microorganisms that break down and recycle matter in an endless cycle. The tectonic plates move and collide and subduct and bring fresh mineral material to the surface, where it weathers into soil, enriching the ground for plants and ultimately for everything that eats plants. Geology, chemistry, biology, oceanography, atmospheric science. All of these disciplines, in some sense, are describing the same thing. The Earth as a system, a web of processes so tightly interwoven that you cannot change one thing without affecting something else. This is not a new idea. The astronomer James Lovelock proposed the Gaia hypothesis in the 1970s. The idea that the Earth's living and non-living components form a single, self-regulating system that maintains the conditions for life. The original formulation went too far in attributing intentionality to the Earth, but the core insight that life does not simply adapt to conditions on Earth, but actively shapes those conditions, has proven enormously fruitful. The oxygen in our atmosphere, for instance, was not always there. Early Earth had an atmosphere rich in methane and carbon dioxide and nitrogen, a reducing atmosphere utterly hostile to the kind of life we know. It was photosynthetic bacteria, cyanobacteria, that, about 2.4 billion years ago, began producing oxygen as a waste product of their metabolic processes. The Great Oxidation Event, as it's called, was one of the most consequential moments in Earth's history. The gradual accumulation of oxygen in the atmosphere transformed the planet, driving many existing anaerobic organisms extinct and setting the stage for the evolution of complex, oxygen-breathing life. The Earth is not just the stage on which life performs. The Earth has been shaped by life, as much as life has been shaped by the Earth. 4 billion years of coevolution have produced the world you see around you. And this world, this ancient, layered, living world, sits in the enormous darkness of space like a lantern. The only lantern, so far as we have yet found, for an unimaginable distance in all directions. Look up on a clear night. There it is, the moon. Steady and pale and seemingly close, like a lantern hung just above the treetops. It is the brightest object in the night sky, second only to the sun in the daytime. It is the companion of every culture that has ever looked up. It has been a calendar, a god, a muse, a mystery. It has guided sailors and inspired poets and pulled at the tides of every ocean on Earth with the quiet, irresistible force of its gravity. It looks close. It is not close. The average distance from the Earth to the Moon is approximately 384,400 kilometers. Let that number breathe for a moment. 384,000 kilometers. If you were to drive there in a car, never stopping, traveling at a comfortable highway speed of 100 kilometers per hour, you would drive for roughly 4.5 months, 24 hours a day, 7 days a week, without rest. You would need to pack a great deal of food. But even that number, that driving analogy, doesn't quite prepare you for the visual, for the emptiness of it. Here is a way to try to see it truly. Take a standard globe, the kind you might find in a classroom or on a desk. The globe that represents the Earth is, depending on the model, somewhere between 20 and 30 centimeters across. If you hold it in your hands, you can feel the whole world in your palms. Now, to represent the moon accurately at the same scale, you would need a small marble, about 7 centimeters across. And you would need to place that marble not 6 inches away from the globe, not a foot away, not even across the desk. You would need to carry it about 7 to 10 meters away, across a medium-sized room, maybe through a doorway, maybe out into a hallway. That gap, that 7 to 10 meters of empty air between the globe and the marble, that is the space between the Earth and the moon. In your mind, stretch that hallway out and fill it with absolute vacuum. No air, no sound, no light, except what bounces off the surfaces. Just the gulf. And yet, we went there. On July 20th, 1969, something happened that had never happened before in the 4-billion-year history of this planet. A living thing, a human being, left the surface of the Earth, crossed that 384,000-kilometer void, and set foot on another world. Neil Armstrong and Buzz Aldrin descended to the surface of the moon in a small, fragile spacecraft, while Michael Collins orbited above in the command module. They were 3 human beings, alone in the most inhospitable environment imaginable. In vehicles that had less computing power than a modern smartphone, sustained by a few hours' worth of oxygen and a system of life support held together by engineering and courage and the accumulated knowledge of an entire civilization. When Armstrong stepped down from the lunar module ladder and placed his boot in the grey lunar dust, he spoke those famous words. Words chosen carefully, meant for history, meant for every human ear that would ever hear them. One small step for man, one giant leap for mankind. And then he looked up. Imagine what he saw. A sky utterly without blue, without clouds, without any of the familiar signals that sky exists at all. Just blackness, dense and absolute, and in that blackness hanging perfectly still. For there is no wind, no weather, nothing moving at all. The Earth, our Earth, a sphere of blue and white, more beautiful than any painting, more vivid than anything imagined, suspended in the dark. Larger than a full moon appears from Earth, silent, still, alive. That view, that singular, impossible view, was the payoff. The accumulated effort of millions of scientists and engineers and workers and dreamers, the expenditure of hundreds of billions of dollars, the risk of human lives. It all led to a moment when a human being could stand on another world and look at home. The moon itself, up close, is a revelation of strangeness. It is a world of extremes. Its surface temperature swings from 127 degrees Celsius in the sunlight to minus 173 degrees Celsius in shadow. There is no atmosphere, no air to carry sound, no sky to scatter light, no wind to erode the surface. A footprint in the lunar regolith will remain perfectly intact for millions of years, undisturbed, unless struck by a meteorite. The terrain is ancient and battered. The craters that pockmark its surface are the scars of impacts stretching back billions of years. A record of the violence of the early solar system, written in stone that has never been weathered away. Mare Imbrium, the Sea of Rains. Named by astronomers who imagined, incorrectly, that these dark plains were oceans, is a vast, ancient lava plain, hardened billions of years ago. It is as old as time itself feels. The moon is not just a physical neighbor, it is our partner. Its gravity stabilizes the tilt of the Earth's axis, keeping it wobbling only slightly rather than tumbling, chaotically. Without the moon, the seasons as we know them might not exist. The great tidal rhythms of our oceans, the intertidal zones, the ecosystems they support, are the moon's gift to us, the steady pulse of its gravitational pull washing the shores twice a day. Even our calendar traces back to the moon. Month comes from moon. The word for Monday is, in many languages, a word that means moon's day. It has been with us so long, shaped our sense of time so deeply, that its language is embedded in the very structure of how we speak. And yet, for all its importance, all its closeness, all its brightness in our sky, the moon is profoundly, startlingly far away on any scale that matters for what comes next. Because from here, the journey expands almost incomprehensibly. The moon is 384,400 kilometers from Earth. Our next destination is 150 million kilometers from where we stand. That is not a typo. The space between us and the sun, the distance that light takes, 8 minutes to cross, is roughly 400 times the distance to the moon. 400 moon distances. If we are going to understand the solar system, if we are going to truly feel its scale, we need to be willing to let go of everything we thought we knew about what far away means. Take a breath. We are only just beginning. There is more to say about the moon, and about what the moon means. When the first Apollo astronauts returned from the lunar surface and were quarantined in the mobile quarantine facility, a converted Airstream trailer, they were met by President Nixon, who stood outside the window and spoke to them through the glass. It was a precaution. NASA scientists genuinely did not know whether the astronauts might have been exposed to some form of lunar contamination, some unknown microorganism or substance that could pose a risk to life on Earth. The precaution seems almost quaint now. The moon is demonstrably lifeless, a world scrubbed clean by billions of years of solar radiation and lacking any of the complex chemistry that life requires. But at the time, the caution was genuine. No human being had ever been to the moon before. No one knew with complete certainty what they might find. This combination of courage and caution, pushing the boundaries of the possible while respecting the unknown, is one of the finest expressions of the scientific spirit. You go to the edge of what is known, and you are careful about what you bring back. The Apollo program produced 12 people who walked on the moon between 1969 and 1972. 12 human beings out of all the billions who have ever lived on this planet have had the experience of looking up and seeing the Earth as a small, distant disk in a black sky. The program was cancelled in 1972, partly for budgetary reasons, partly because the political goals, demonstrating American technological superiority over the Soviet Union, had been achieved. The remaining Apollo missions were cut. We have not been back. Not yet. 50 years have passed since a human footprint was last pressed into the lunar dust. Those footprints, still there, slowly being eroded only by the gentle rain of micrometeorites, are among the loneliest things in the solar system. Silent testimony to a brief moment when human beings reached out and touched another world. The moon has never been only about exploration or politics. It has been, for the entire length of human existence, a source of wonder. The monthly cycle of the moon, new moon to full moon and back, was almost certainly the first regular calendar that any human community used. The moon was there before language, before agriculture, before the first cities. It was there when our ancestors crouched around fires and looked up at the sky and began to ask questions about what they saw. It has changed very little since then. A few craters here and there added by impacts over the last few thousand years. The thin, powdery regolith on the surface, gardened by micrometeorites, slowly churning on timescales of millions of years. But essentially, the same moon that our earliest ancestors knew. The same craters, the same dark Maria, the same gentle phases, the same pale light cast over sleeping fields and forests and oceans on countless clear nights throughout all of human time. There is continuity in that, a thread connecting you to every human being who has ever looked up and seen the moon. When you look at it tonight, and you should, you are sharing the experience with everyone who has ever lived. The moon is humanity's oldest companion in the sky. Now let us try something. Let us build a scale model of the solar system in your mind. A true scale model, accurate in every dimension so that you can actually feel what our solar system is. Find a large, open field, something at least 10 kilometers wide. Place a grapefruit in the center of the field. That grapefruit, about 12 centimeters across, represents the sun at this scale. Now, the sun. The actual sun has a diameter of approximately 1.4 million kilometers. If you stood the Earth on one side of the sun and placed another Earth on the other side, you could fit 109 Earths across the sun's diameter. And if you hollowed out the sun and filled it with copies of the Earth, you could fit roughly 1.3 million of them inside. It is a staggering thing to try to imagine. The sun is not merely a larger version of the Earth, it is a different category of object entirely. From its surface to its center, it spans almost 700,000 kilometers of churning plasma, nuclear furnace, magnetic fury. At its core, temperatures reach 15 million degrees Celsius, and the pressure is so intense that hydrogen atoms are fused together into helium at a rate that generates, every single second, more energy than humanity has produced in its entire history. The sun is, in every practical sense, everything. It provides 99.8% of all the mass in the solar system. Its gravity controls the motions of everything from Mercury to the outermost fragments of ice in the Oort cloud, billions of kilometers away. Without it, there would be no solar system, only a cold, dark scatter of rocks and gas drifting through interstellar space. Now, on our scale model, where you have placed your grapefruit sun in the center of the field, Mercury, the smallest planet and the closest to the sun, would be a barely visible poppy seed, about 2 millimeters wide, hovering about 5 meters away from the grapefruit. Stand beside your grapefruit sun and hold out your arm. Mercury is at the tip of your fingers. Mercury is, in reality, about 57.9 million kilometers from the Sun on average. It is a world of extremes: scorching days, frigid nights, a surface so cratered and ancient it looks frozen in time. Its year, the time it takes to orbit the Sun, is only 88 Earth days. It moves quickly through the sky for those who observe it, sprinting around its tight, elliptical orbit, always close to the blinding glow of its star. Venus, the second planet, sits on our scale model about 10 meters from the grapefruit Sun, another small seed, very similar in size to the Earth seed, roughly 2 millimeters. In reality, Venus is about 108 million kilometers from the Sun, and it is in many ways Earth's twin in size and composition. But the resemblance ends there. Venus is a hell world. Its atmosphere is 90 times denser than Earth's, composed mostly of carbon dioxide with clouds of sulfuric acid. Its surface temperature averages 465 degrees Celsius, hot enough to melt lead. The pressure at the surface would crush any unprotected human being instantly. Venus is what happens when a greenhouse effect runs completely unchecked. A cautionary tale inscribed in planetary geology. Walk 15 meters from your grapefruit Sun on the DMI scale model. There is the Earth, a small blue-green seed, 2 millimeters across. Attached about a centimeter away at this scale, orbits the slightly smaller grey seed of the Moon. In reality, you are standing 150 million kilometers from the Sun. This distance, Earth's average distance from the Sun, is so fundamental to astronomy that it has its own name: 1 astronomical unit, or AU. It is the yardstick of the solar system. Continuing outward on your scale model, Mars sits about 22 meters from the grapefruit Sun, a reddish seed, about half the size of Earth at this scale. In reality, Mars orbits at an average distance of 228 million kilometers, or about 1.5 astronomical units. Mars is our best neighbor for potential human exploration. It has seasons. It has a day nearly the same length as Earth's. It has a thin atmosphere, ancient river valleys, polar ice caps, and towering volcanic mountains. Olympus Mons, the tallest mountain in the solar system, rising 21 kilometers above the surrounding plains. Between Mars and Jupiter lies the asteroid belt, not the dense, dangerous cloud of Hollywood imagination, but a remarkably sparse collection of rocky and metallic fragments spread across an enormous volume of space. If you could gather all the material in the asteroid belt and compress it together, it would form an object smaller than our Moon. The belt exists because Jupiter's immense gravity prevented its material from ever coalescing into a planet. It is a might-have-been world scattered to the winds. Now walk farther from your grapefruit Sun. Keep walking. Walk 78 meters from the center of the field. Here is Jupiter, the king of the planets. A marble-sized sphere at this scale, but in reality, 142,984 kilometers across. Jupiter is enormous. It is larger than all other planets in the solar system combined, and then some. Its mass is 318 times that of Earth. Its famous Great Red Spot, a storm that has been raging for at least 400 years, is larger than the entire Earth. Jupiter is at 5.2 astronomical units, about 778 million kilometers from the Sun. Jupiter's system is a world unto itself. It has at least 95 confirmed moons, 4 of which, Io, Europa, Ganymede, and Callisto, are so large they would qualify as planets if they orbited the Sun directly. Europa is of particular fascination to scientists. Beneath its icy shell, a vast liquid water ocean may exist, warmed by tidal forces from Jupiter's gravity. If life can exist anywhere in the solar system beyond Earth, Europa is one of the most compelling candidates. Walk 143 meters from your grapefruit sun. Saturn, another marble at this scale, slightly smaller than Jupiter, but ringed by a magnificent structure that makes it instantly recognizable from anywhere in the sky. Saturn's rings are made of billions of individual pieces of ice and rock, ranging in size from tiny dust grains to chunks as large as houses. They extend hundreds of thousands of kilometers from the planet's surface, yet they are typically only about 10 to 100 meters thick. The rings are at once immense and impossibly thin, like a razor blade stretched across space. In reality, Saturn is 1.4 billion kilometers from the Sun. Light takes 1 hour and 20 minutes to travel from the Sun to Saturn. The Cassini spacecraft, one of humanity's greatest robotic missions, spent 13 years orbiting Saturn and sent back data and images of incomprehensible beauty. The rings in delicate detail, the moons in close-up, the hexagonal polar storm that has spun at Saturn's North Pole for decades. Uranus and Neptune are the ice giants. Worlds of frozen methane and ammonia and water, their blue-green hues the result of methane gas absorbing red light in their atmospheres. They were the last planets discovered by direct observation. Uranus first in 1781, Neptune in 1846. Neptune is roughly 30 astronomical units from the Sun, about 4.5 billion kilometers. On your scale model, it sits nearly 300 meters from your grapefruit sun. You have crossed an entire field. Light takes 4 hours to travel from the Sun to Neptune. If you shone a flashlight from Earth toward Neptune, you would be dead of old age before most of the beam made its journey. Well, not quite, but the time scale of communication across the solar system is measured in hours. When NASA scientists sent commands to Voyager 2, which flew by Neptune in 1989, they waited 4 hours for the signal to travel from Earth to the spacecraft. 4 hours of silence while the commands crossed the solar system. And beyond Neptune, beyond the last of the classical planets, there is more, far more. The Kuiper Belt is a vast region of the outer solar system extending from Neptune's orbit out to about 50 astronomical units. It is populated by icy bodies, the remnants of solar system formation that never gathered into planets. Pluto, poor Pluto, reclassified. In 2006 as a dwarf planet and source of considerable public outrage, resides in the Kuiper Belt, about 40 astronomical units from the Sun. It has 5 moons, the largest of which, Charon, is so big relative to Pluto that the two form a binary system, orbiting a common center of gravity that lies in the space between them. The Kuiper Belt is vast, but it is not the edge. Beyond it, in a region we have never directly observed, lies the Oort cloud. The Oort cloud is a theoretical shell of icy bodies thought to surround the solar system at enormous distances, beginning perhaps at 2,000 astronomical units and extending perhaps to 100,000 astronomical units or more. It is, in the truest sense, the outer boundary of the Sun's gravitational influence. Comets, those long-tailed visitors to the inner solar system that have been portents and omens in every human culture, originate here. Something disturbs them, perhaps a passing star, and they fall inward on long, elliptical orbits, taking thousands of years to journey from the cold darkness of the Oort cloud to the warmth of the inner solar system, where they develop their brilliant tails as solar heat sublimates their ices. The Oort cloud has never been directly observed. It is too distant, too sparse, too cold. We infer it from the comets it sends us, the gravitational logic of its existence. It is a hypothesized realm, but a realm whose existence is supported by every comet that has ever blazed across our sky. On your scale model, the outer Oort cloud would extend to perhaps 700 kilometers away from your grapefruit sun. Not 700 meters, 700 kilometers. Your 10-kilometer field is not even a thousandth of the way across the full extent of the sun's family. The solar system, from center to outer Oort cloud, spans about 2 light years. 2 years of travel at the speed of light. To cross it in a spacecraft like the Voyager probes, traveling at about 17 kilometers per second. The fastest human-built objects ever made. Would take approximately 30,000 years. 30,000 years. When the Voyager probes were launched in 1977, human civilization had existed in its earliest agricultural forms for only about 12,000 years. The pyramids were being built a mere 4,000 years ago. All of recorded human history fits into a fraction of the time it would take a Voyager-speed spacecraft to cross from one side of the solar system to the other. And after all that travel, after those 30,000 years of darkness and cold, the spacecraft would still be in the neighborhood of the sun. Still inside our own star's gravitational territory. Still, in the deepest sense, home. Because beyond the Oort cloud, beyond the last whisper of the sun's dominion, lies something that makes the solar system seem intimate, almost cozy, interstellar space. There is something poetic about the asteroid belt that deserves a moment of pause. It represents a road not taken, a world that might have been. In the early solar system, the material between Mars and Jupiter was gathering, slowly, under the pull of gravity, beginning the long process of accretion that had already produced the inner planets. But Jupiter, enormous, dominant, its gravity many times the force of any other planet in the solar system, kept stirring things up. Its gravitational influence created resonances in the orbits of the accumulating material, ensuring that whenever objects in the belt began to grow large enough to start gathering mass in earnest, Jupiter's tidal forces would disrupt them, strip material away, prevent the formation of a stable large body. The asteroid belt, then, is both a reminder of Jupiter's dominance and a historical record of the early solar system. The rocky metallic objects within it, ranging from tiny dust grains to the dwarf planet Ceres, which is about 940 kilometers across, are primordial. They have barely changed in 4.5 billion years. When spacecraft visit them, they are visiting the raw material of planet formation, preserved in cold storage since before the Earth existed. Ceres itself is worth a moment of thought. It is the only dwarf planet in the inner solar system. It contains roughly a third of the total mass of the asteroid belt. The Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed a world with bright spots of sodium carbonate in its craters. Evidence of salty water that once flowed there, or perhaps still does, in some subsurface reservoir. Ceres, like Europa, like Enceladus, like so many worlds in our solar system, hints that water, and perhaps the chemistry of life, is more widespread than we might initially expect. Saturn's rings, too, deserve deeper contemplation. They are transient on geological timescales. Saturn has probably had several different ring systems over its history, as moons were broken apart and the rings gradually spread and dissipated. The current rings are estimated to be only about 100 million years old, young by solar system standards. When the dinosaurs were still walking the Earth, Saturn may have appeared quite different in the sky of any beings who might have been watching. The rings we see now, their particular structure and brightness and pattern, those are a fortunate accident of timing. There is something humbling in that. We got here just in time to see Saturn's rings in their current glory. 1 billion years from now, they may be largely gone, and no one who sees them then will know what was lost. The outer solar system beyond Saturn has a strange, cold beauty. Uranus rolls on its side, rotating nearly perpendicular to its orbital plane, the result of a massive collision in its ancient past. Its rings are dark and narrow, utterly unlike Saturn's. Its moons are named after characters from Shakespeare and Alexander Pope. Neptune, the most distant of the classical planets, blue-green and stormy, has winds that reach 2,000 kilometers per hour, the fastest in the solar system. Its moon Triton orbits in the opposite direction to most moons, and geysers of nitrogen erupt from its poles. The first confirmed geysers ever observed off Earth. The solar system is full of such surprises, full of individual worlds, each with its own story, its own history, its own strange particulars. We have sent spacecraft to all 8 planets and many of their moons. We have landed on Mars and Venus. We have flown through the rings of Saturn. We have photographed Pluto in breathtaking detail. And still, every new mission reveals something unexpected, something that challenges our models and expands our understanding. The solar system is not a simple, static arrangement of objects. It is a dynamic, ever-changing family of worlds, shaped by billions of years of collisions and migrations and gravitational dances, still evolving, still surprising us. You have walked to the edge of the solar system in your mind. Behind you, incredibly far away, is the grapefruit sun. Around you, the Oort cloud extends its sparse veil of icy nomads. Ahead of you, in every direction, in all the 3 dimensions of space, is the void. Let us think carefully about what void means here. In everyday language, a void is an absence, a lack of something. A hole in a wall is a void. An empty drawer is a void. But these words are too small, too human-scaled to describe what interstellar space actually is. The space between stars is not merely empty. It is empty in a way that has no analogy in human experience. In the best vacuum humans have ever produced in a laboratory, there are still a few thousand atoms per cubic centimeter. In interstellar space, the average density of matter is about 1 atom per cubic centimeter. Sometimes less, sometimes far less. In the spaces between galaxies, intergalactic space, the density drops to perhaps 1 atom per cubic meter, a cubic meter of almost perfect nothingness. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system, which lies approximately 4.24 light-years away. 4.24 light-years. Let's make sure we understand what a light-year is before we go further, because this unit of distance is going to be our companion for the rest of this journey. A light-year is the distance that light travels in 1 year, not the time it takes, the distance. Light moves at approximately 300,000 kilometers per second. In 1 minute, it covers about 18 million kilometers. In 1 hour, roughly 1.08 billion kilometers. In 1 year, 1 year of constant, unimaginable speed. Light covers about 9.46 trillion kilometers. 9.46 trillion kilometers. Or, in the units we used before, about 63,241 astronomical units. About 63,000 times the distance from the Earth to the Sun. About 163 times the diameter of the outer solar system, as defined by the major planets. Alpha Centauri is 4.24 of those years away. That is 40 trillion kilometers. 40,000 billion kilometers. If you took the diameter of the Sun, already incomprehensibly large, and laid it end to end across that distance, you would need to use it 4 million times to get from here to there. On the scale model you built earlier, the one where the Sun was a grapefruit, Alpha Centauri would be another grapefruit sitting approximately 4,700 kilometers away. If you placed your grapefruit sun in one city, your nearest stellar neighbor would be in another country. No human-built object has ever come close to reaching Alpha Centauri. The Voyager 1 spacecraft, the most distant human-made object, is currently about 23 billion kilometers from the Sun, roughly 160 astronomical units. That is extraordinary. It is awe-inspiring. And it is also about 0.06% of the way to Alpha Centauri. If Voyager 1 were heading toward Alpha Centauri, which it isn't exactly, it would arrive in approximately 73,000 years. 73,000 years. The agricultural revolution was about 10,000 years ago. Homo sapiens as a species has only existed for about 300,000 years. The entire span of recorded human civilization, Egypt, Rome, the Renaissance, the Industrial Revolution, the Space Age, fits within a single geological eye blink. And the nearest star is 73,000 Voyager years away. The Breakthrough Starshot Initiative, one of the most ambitious scientific proposals of our era, has proposed launching tiny, laser-propelled probes to Alpha Centauri at roughly 20% of the speed of light. At that speed, the journey would take about 20 years. Even this extraordinary vision, if realized, represents travel at speeds utterly beyond any technology currently available. And the probes would be the size of a postage stamp, carrying cameras and communication equipment reduced to microscopic scales. 20% of the speed of light, 300,000 kilometers per second, is light speed. 20% of that is 60,000 kilometers per second. In the time it takes you to read this sentence, such a probe would travel roughly 600,000 kilometers. It would cross the distance to the moon in about 6 seconds. Even at this extraordinary speed, the journey to the nearest star takes 20 years. One human generation of patience and waiting, just to reach the very nearest neighbor in the cosmic neighborhood. The galaxy is full of stars separated by distances like this. Most of them are even farther away than Alpha Centauri. The stars in the night sky, the ones you see with your naked eye, the ones you have named and told stories about, are mostly between 100 and 1,000 light years away. Their light, when it reaches your eye, is old. It left those stars decades, centuries, millennia ago. You are not seeing those stars as they are now. You are seeing them as they were. The night sky is not a window into the present. It is a window into the past. Rigel, the brilliant blue-white star in the shoulder of Orion, is about 860 light-years away. The light entering your eye from Rigel tonight left that star around the year 1165. During the High Middle Ages, when the Crusades were being fought in the Holy Land and the first universities were being founded in Europe. Rigel itself might have changed in the intervening 8.5 centuries. We have no way of knowing. Betelgeuse, the famous red supergiant in Orion's shoulder, is about 700 light-years distant. It is a variable star, pulsing and dimming unpredictably. Astronomers have long speculated that Betelgeuse will eventually go supernova, an explosion of almost incomprehensible energy, briefly outshining the entire galaxy. When it does, it will be visible in daylight from Earth. But when it does explode, the light telling us that it has exploded will take 700 years to reach us. Betelgeuse may already have exploded. The light may be on its way right now, streaming toward us at the speed of light, carrying news of a stellar death that happened centuries ago. We are receiving a universe of news that is always delayed, always old, always a message from a past that no longer exists in the form we see it. This is not merely a quirk of astronomical observation. It is a fundamental feature of reality. Information cannot travel faster than light. The universe enforces this limit absolutely. And because the universe is large, and because information takes time to cross it, everything we see is a version of the past. Looking deeper into space means looking further back in time. The night sky is a time machine in the darkness between the stars, in the immense, cold, silent space that stretches from the edge of the solar system to the surface of the nearest stellar world. There is almost nothing. No planets, no comets, no dust clouds of significance. Just space. And in that space, the faint, invisible threads of magnetic fields and the occasional lone hydrogen atom, drifting without purpose, without destination, through a darkness that has not been warm since the universe was young. This is where we are, in a universe where the spaces between things are almost everything, where matter, all the stars and planets and moons and asteroids and comets and dust clouds, is a thin, improbable frosting on an enormous dark cake. And we have not even begun to grasp the true scale of things, because all of this, the sun, the planets, the Oort cloud, and the vast silence of interstellar space all the way to Alpha Centauri and beyond, all of it fits inside a single galaxy. Our galaxy, the Milky Way. And the Milky Way is just the beginning. Let us pause in interstellar space for a moment longer, because it is worth truly trying to inhabit this silence. You are in your imagination, somewhere between the stars. Behind you, the solar system is invisible. The sun is a bright star, the brightest in the sky from here, but it is just a star. The planets are completely invisible, far too small and faint to detect against the background of stars. You are in a region where the nearest solid surface might be light years away in any direction. There is no sound. There has never been sound here. Sound requires a medium to travel through, and the interstellar medium is so thin, a few atoms per cubic centimeter at best, that no pressure wave can travel through it at any meaningful speed. The vacuum of interstellar space is not the vacuum of a theatrical play, filled with tense silence. It is a silence so absolute that the word silence doesn't quite fit. It is the absence of the possibility of sound. The temperature here is about minus 270 degrees Celsius, just a few degrees above absolute zero, warmed slightly by the cosmic microwave background radiation that fills all of space uniformly in all directions. There is no local source of heat. The starlight falling on you from all directions is negligible. You would radiate heat until you matched the temperature of the background radiation, and then you would remain frozen in the dark. And yet, this emptiness is not truly empty in another sense. The interstellar medium, the thin gas and dust that fills the space between stars, is far more chemically complex than you might expect. Astronomers have detected more than 200 different molecules in interstellar space, including water, ammonia, methanol, formaldehyde, and, to the great excitement of astrobiologists, amino acids, the building blocks of proteins. Complex organic chemistry occurs in the cold, dark reaches of space, catalyzed by the surfaces of dust grains and energized by ultraviolet radiation. This suggests something profound. The chemistry of life is not uniquely terrestrial. The building blocks of life, or at least the precursor molecules from which life's building blocks can be assembled, are present throughout the galaxy, drifting in the cold dark of interstellar space, waiting to be concentrated in the warm interiors of planetary systems, in the liquid water of ocean worlds, in the chemistry of planetary atmospheres. When comets fall inward from the outer solar system and strike young planets, they bring with them not just water, but organic molecules accumulated over millions of years in the interstellar medium. The carbon-rich chemistry of life on Earth may owe something to this cosmic delivery system. to the cold laboratories of interstellar space, working their organic chemistry across millions of years in the dark between the stars. The silence of interstellar space is full of chemistry. The emptiness is not empty, and in the long timescales of cosmic history, patience is rewarded. The molecules form, the comets fall, the worlds warm. And sometimes, perhaps often, perhaps rarely, we do not yet know, life begins. We are the product of interstellar chemistry as much as we are the product of Earth's oceans and sunlight. We carry the cosmos in our molecules. Step back further. Further than any spacecraft has gone, further than any probe, further than any telescope, can directly show us in full. Step back until the sun becomes just one more point of light among many. Step back until the solar system vanishes into the crowd. Step back until you can see the whole thing at once. What you would see if you could somehow step outside our galaxy and look back is a disk. A beautiful, slowly rotating disk of stars and gas and dust, about 100,000 light-years across and roughly 1,000 light-years thick at its outer edges, thickening to about 10,000 light-years at the central bulge. It is spiral in structure, sweeping arms of denser star formation curling outward from a central hub, lit from within by the combined light of hundreds of billions of suns. The Milky Way contains somewhere between 100 and 400 billion stars. That range, that uncertainty of 300 billion, illustrates how hard these numbers are to pin down. We estimate by sampling regions and extrapolating. The true number is probably somewhere in there, perhaps 250 billion, perhaps more, 250 billion stars. Stand outside on a dark night, away from city lights, and look up at the Milky Way, that luminous dusty band arching across the sky. That is our galaxy, seen edge on from the inside. The light you see is the combined glow of billions of suns, so far away that they blur into a continuous shimmer. You are seeing your home. Not Earth, not the solar system, your galactic home. The Milky Way is where we live. And where exactly do we live within it? We are not at the center. The center of the Milky Way, a dense, spectacular, violent region of stars and gas and ancient light, is about 26,000 light-years away from us. We are in the outer suburbs, about halfway out from the center to the edge, embedded in one of the spiral arms called the Orion Arm, or the local spur. We are not particularly close to any major feature. We are just here, in an unremarkable corner of a magnificent galaxy. From our position, it takes the solar system about 230 million years to complete one orbit around the galactic center. This period is sometimes called a cosmic year, or a galactic year. In the entire existence of our solar system, about 4.6 billion years, we have made the trip around the galaxy roughly 20 times. While the last dinosaurs were becoming extinct, our solar system was in a completely different position in the galaxy than it is now. When the Earth first formed, we were on the other side. The center of the Milky Way is a region of spectacular density and violence. Stellar nurseries bloom there, vast clouds of gas and dust, where new stars are born by the millions. Ancient, tightly packed clusters of old red stars surround the center in a dense spherical halo. And at the very heart of the Milky Way, at the center of everything, hidden behind vast clouds of dust that block all visible light, there is a monster, Sagittarius A star, a supermassive black hole, approximately 4 million times the mass of our Sun, crammed into a volume smaller than our solar system. It is quiet by the standards of active galactic nuclei. It is not currently consuming vast amounts of matter, So it is not blazing with the accretion disk radiation that makes some galactic centers among the brightest objects in the universe. But it is there. It has always been there. Its gravity is woven into the motion of every star in the inner galaxy. In April 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole shadow. The supermassive black hole at the center of the galaxy, M87 55 million light-years away. And in May 2022, they released an image of Sagittarius A star itself, our own galactic center's black hole, captured for the first time in visible form. A glowing ring of superheated gas surrounding a central darkness. The shadow of a thing 4 million times the mass of the sun. Looking at that image is one of the stranger experiences available to a modern human being. You are looking at the center of your galaxy. You are looking at an object that has been there since the galaxy itself formed over 13 billion years ago. You are looking at a thing that bends space-time itself around it, from which nothing, not light, not information, not any signal of any kind, can ever escape. It is 26,000 light-years away. The light in that image left Sagittarius A star 26,000 years ago, when our ancestors were painting animals on cave walls by firelight, when the great glaciers of the last ice age were only beginning to retreat. That ancient light crossed the galaxy, passed through clouds of gas and dust, and fell onto telescopes built by beings who could not have imagined their own existence when that light began its journey. Beyond the disk of the Milky Way, there is a halo, a vast, roughly spherical region extending perhaps 100,000 light-years in all directions from the galactic center. The halo contains old globular clusters, tight, brilliant spheres of hundreds of thousands of ancient stars, some of them nearly as old as the universe itself. And it contains something we cannot see at all, but whose gravitational presence shapes everything: dark matter. Dark matter. It neither emits, reflects, nor absorbs light. It cannot be detected directly by any instrument we have yet built. And yet, from the motions of stars within galaxies and galaxies within clusters, from the large-scale structure of the cosmos and the patterns of the cosmic microwave background, we know it is there. We know it comprises roughly 27% of the total energy content of the universe. We know it forms a vast web of invisible scaffolding within which ordinary matter, stars, gas, planets, us, is embedded like foam in a framework of invisible wire. The Milky Way's dark matter halo extends perhaps 1 million light-years from the galactic center, 10 times the size of the visible disk. It is massive, filling the space around our galaxy with substance we can feel but never see. The Milky Way is, in short, not just the band of stars you see on a clear night. It is not just the 250 billion suns you might count if you had time and eyes bright enough. It is also a vast halo of dark matter, a thin spherical shell of ancient stellar clusters, and at its heart, a sleeping monster that has shaped the history of everything within its reach. It is our galaxy. It is our home. And now, having truly tried to feel its scale, having tried to imagine 100,000 light-years of stars and gas and darkness and dark matter, we must begin to zoom out again. Because the Milky Way is only one of something. And that something is so numerous, so enormous that the Milky Way, for all its hundreds of billions of stars, begins to seem like a modest thing. Modest and dear. The stars of the Milky Way are not uniformly distributed. They form structures within the galaxy, patterns that reflect the history of star formation over billions of years. The spiral arms, Sagittarius, Perseus, the Orion arm where we reside, and others, are regions of denser gas and dust, where the pressure waves that travel through the galactic disk like ripples on a pond have compressed the interstellar medium enough to trigger the formation of new stars. The bright, hot, young blue stars that trace the spiral arms are born there, live their brief, brilliant lives, and die there, enriching the interstellar medium with the heavy elements their nuclear furnaces have synthesized. The cycle of stellar life and death is one of the most profound in all of nature. Stars are born in clouds of gas and dust, nebulae, when a region of the E cloud reaches sufficient density that gravity overcomes the pressure and begins to collapse. As the cloud collapses, it heats up. At the center, the temperature and pressure rise until nuclear fusion ignites and a star is born. The surrounding material either falls inward or forms a disk, a protoplanetary disk, that may eventually coalesce into planets. The star burns for millions or billions of years, depending on its mass. Massive stars, 10, 50, 100 times the mass of the Sun, burn intensely and die quickly in millions of years. Smaller stars like the Sun burn steadily for 10 billion years. The smallest stars, red dwarfs, burn so faintly that they can last for trillions of years, longer than the current age of the universe. When a star like the Sun nears the end of its life, it swells into a red giant, expanding enormously, engulfing its inner planets, exhausting its hydrogen and then its helium fuel. Eventually, it sheds its outer layers in a beautiful, expanding cloud of glowing gas called a planetary nebula. A misnomer given by early observers who thought these glowing rings resembled planetary disks through early telescopes. And its core collapses into a white dwarf, a dense, cooling remnant about the size of the Earth, composed mostly of carbon and oxygen, no longer generating energy through fusion, slowly cooling over billions of years toward darkness. More massive stars end more dramatically. When their fuel is exhausted, their cores collapse suddenly, triggering a supernova. An explosion that, for a brief moment, can outshine an entire galaxy. The shockwave sweeps through the surrounding interstellar medium, compressing it, triggering new generations of star formation. The heavy elements forged in the star's core, elements like iron, nickel, silicon, are scattered into space, enriching the gas and dust with the raw materials of planets and life. The atoms in your body have been through this cycle. The carbon in your cells was forged in the nuclear burning of stars. The iron in your blood was made in the core of a massive star and scattered by its supernova death. The oxygen you breathe was processed by multiple generations of stars before the solar system formed. You are not merely made of star stuff in a metaphorical sense. You are literally recycled stellar debris, matter that has been through the furnaces of previous stellar generations and emerged, reorganized by chemistry and biology, into a form that can contemplate its own origin. The Milky Way has been making stars for most of its 13 billion year history. The oldest stars in the galaxy, found in the globular clusters of the halo, are nearly as old as the universe itself. The Sun, at 4.6 billion years old, is a relatively young citizen of the galaxy. Younger still are the blue supergiants blazing in the spiral arms, burning so fiercely that they may live for only a few million years before their inevitable, spectacular ends. In this context, the existence of any particular star or planet or living world is fragile and contingent. The product of a specific moment in a specific part of the galaxy, dependent on the history of star formation that preceded it and the particular conditions of the interstellar cloud from which it formed. The solar system exists because, about 5 billion years ago, a region of gas and dust in the Orion Arm was compressed. perhaps by the shockwave of a nearby supernova, and began to collapse. That collapse led over millions of years to the Sun and the planets. The supernova that may have seeded our solar system's formation was, in a very real sense, a prerequisite for our existence. We are the children of a dead star. There is a word that astronomers and physicists use sometimes when they are trying to describe what the universe has done, what it continues to do, in the face of entropy, gravity, and the relentless passage of time. That word is structure. The universe has made structure. It has taken what began as a nearly featureless, nearly uniform hot plasma, a broth of energy and simple particles, and organized it over billions of years into stars and planets and galaxies and clusters and superclusters and the cosmic web. Into us. This is not trivial. The second law of thermodynamics tells us that entropy, disorder, increases over time in closed systems. The universe tends toward greater disorder, and yet we see, everywhere around us, spectacular order. Crystals forming, snowflakes assembling themselves into complex symmetry, stars burning, planets orbiting, life organizing matter into bodies and brains. The resolution of this apparent paradox is that local order, local decreases in entropy, are possible as long as they are accompanied by greater increases in entropy elsewhere. The Sun pours energy into the solar system, and life on Earth uses that energy to build complex structures, but in doing so, it radiates waste heat into the cold of space, increasing the total entropy of the universe. The Sun is burning through its hydrogen, converting it irreversibly to helium, and will eventually exhaust its fuel and die. The order we see locally is powered by the greater disorder playing out on cosmic scales. We are, in a sense, eddies in the flow of entropy. Temporary structures maintained against the tendency toward disorder by the constant input of energy from the Sun. When that energy ceases, when the Sun dies, when the stars go out one by one, the temporary structures will dissolve, and the universe will move inexorably toward its final state of maximum entropy. A cold, dark, uniform expanse of slowly decaying matter. But that is far away. Billions and billions of years away. In the meantime, we are here, astonishingly complex and temporarily ordered, burning our small portion of the universe's energy budget, making art and science and music and love, asking questions the universe has never heard asked before. The fact that we exist at all, the fact that the universe made complexity, is not guaranteed by the laws of physics alone. It required specific conditions, the right balance of forces, the right cosmic constants, the right initial conditions. Change the strength of gravity slightly, and stars never form. Change the strong nuclear force slightly, and atoms are impossible. Change the cosmological constant, and the universe either collapses before galaxies can form, or expands so quickly that matter can never concentrate enough to produce stars. We live in a universe that made us. Whether that means anything, whether it implies design or purpose, or is simply an observation about the universe we happen to inhabit, is a question philosophy and theology have been wrestling with for as long as there have been humans to ask it. Science cannot answer it directly, but science can describe, in extraordinary detail, the chain of events that led from the Big Bang to the moment you are reading these words, and in that chain there is something that deserves, at minimum, quiet astonishment. The universe made beings who wonder about it. That is enough to wonder about. You know the feeling of being on an island, or if you don't, you can imagine it. Standing at the water's edge, looking out at the ocean, seeing nothing but sea and sky in every direction. The island feels complete. contained. There is something there, and then there is the water, and somewhere over the horizon is another piece of land. But the water between is immense. The other island, if it exists, is far beyond sight. Galaxies are like that, not islands in water. Islands in the cosmos, separated by gulfs of space so enormous that our minds genuinely cannot grasp them without tools, without metaphor, without great effort. The nearest galaxy to the Milky Way, a substantial one, a galaxy in its own right, is the Andromeda Galaxy, also known as M31 or NGC 224. It is a spiral galaxy, broadly similar to the Milky Way, and it lies approximately 2.537 million light-years from us. 2.5 million light-years. On your scale model, the one where the Milky Way is a grapefruit-sized disk, the Andromeda Galaxy would be another grapefruit sitting about 25 meters away. Two galaxies, each containing hundreds of billions of stars, separated by a corridor of void that light takes 2.5 million years to cross. On a very dark, clear night, away from city lights with good eyes, you can actually see Andromeda. It appears as a faint, fuzzy smudge in the constellation Andromeda, a little larger in apparent size than the full moon, but far, far fainter. What you are seeing with your naked human eyes, unaided, is the combined light of 1 trillion stars, 2.537 million light-years away. You are seeing something that, if your eyes were more sensitive, would dominate the night sky. The light from Andromeda that reaches your eye tonight left that galaxy 2.537 million years ago. At that time, on Earth, the genus Homo was just beginning to appear. Our earliest human ancestors were not yet fully human. They were making simple stone tools, walking upright, but thinking and communicating in ways we cannot fully reconstruct. The Andromeda Galaxy has been sending us that light across the void for longer than our genus has existed. The Milky Way and Andromeda are gravitationally bound to each other. They are not drifting away on the expansion of the universe. They are falling toward each other. Their mutual gravity has been pulling them together across billions of years of cosmic history, and in approximately 4.5 billion years, roughly the current age of the Earth, they will collide. The collision will be unlike anything in human experience. Galaxies, for all their hundreds of billions of stars, are so vast and their stars so widely separated that when two galaxies collide, the stars themselves almost never actually hit each other. Instead, the galaxies will pass through each other, drawn together by gravity, drawn apart by momentum, drawn together again, slowly merging over hundreds of millions of years into a single, large, elliptical galaxy, sometimes called Milkomeda or Milkdromeda by astronomers with a taste for portmanteau. The gravitational distortions during this collision will be beautiful and violent in equal measure. Gas clouds will compress and ignite with a burst of new star formation. Tidal streams of stars will arc through space in elegant curves, hundreds of thousands of light-years long. The spiral arms of both galaxies will distort and shred and gradually dissolve into the smoother, rounder shape of an elliptical. Our solar system, if it still exists in 4.5 billion years, will likely be flung into a completely different region of space, though the Sun itself is unlikely to be significantly affected by any stellar encounter. In the meantime, the Milky Way and Andromeda are not alone. They are the two largest members of what astronomers call the local group, a collection of more than 50 galaxies bound together by gravity, occupying a region of space roughly 10 million light-years across. Most of the members of the local group are small. The Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud, are two irregular galaxies visible from Earth's southern hemisphere, companions to the Milky Way, slowly being disrupted by our galaxy's gravity as they orbit it. The Large Magellanic Cloud is about 160,000 light-years away. It contains a spectacular star-forming region called the Tarantula Nebula, which is so active that if it were located at the distance of the Orion Nebula, our own nearby stellar nursery, it would cast shadows on Earth at night. There are also numerous dwarf galaxies scattered around the Milky Way, small, dim collections of stars that are being slowly absorbed into our galaxy's gravitational influence. Some of them are already being torn apart, their stars scattered into streams that wrap around the Milky Way in ghostly arcs. The local group, in turn, is one of many galaxy groups in a larger structure. And here we begin the next zoom out, from individual galaxies to the great city-states of the cosmos, the galaxy clusters. The story of galaxy mergers is one that is written in the sky for anyone who knows how to read it. Look at the antennae galaxies, a pair of spiral galaxies, NGC 4038 and NGC 4039, caught in the act of collision about 70 million light-years from Earth. Their images, captured by the Hubble Space Telescope and others, are among the most dramatic in all of astronomy. Two galactic disks interpenetrating, vast tidal tails of stars streaming outward in graceful curves, hundreds of thousands of light-years long. Brilliant blue clusters of newly formed stars blazing in the compressed gas of the collision zone. Ancient red stars scattered in widening halos around the distorted cores. This is the future of the Milky Way and Andromeda, written in another pair of galaxies. This is what we are falling toward, what awaits us in 4.5 billion years. But step back further and consider, what does it mean for two galaxies to collide? It is not like two billiard balls striking each other, crashing and shattering. It is more like two clouds of fireflies drifting through each other in the dark, each firefly following its own path, influenced by the collective gravity of all the others, but almost never actually encountering one individually. The stars of two colliding galaxies pass through each other's space like ghosts passing through walls, occupying the same volume but barely interacting directly. What does interact powerfully is the gas, the diffuse clouds of hydrogen and helium that fill the space between stars in both galaxies collide directly. Shock heat, compress, and in the compressed regions, new stars ignite by the millions. Galaxy mergers are among the most prolific star-forming events in the universe. The antennae galaxies are currently producing new stars at a rate far exceeding that of either parent galaxy in its normal state. And at the cores of both merging galaxies, the supermassive black holes, which every large galaxy seems to have at its center, are drawn together by gravity, circling each other in a long, slow in-spiral. Billions of years from now, they will merge, producing a single, more massive black hole, and in the process emitting gravitational waves. Ripples in space-time itself, propagating outward at the speed of light, carrying energy away from the system. Gravitational waves from black hole mergers are now routinely detected on Earth by the LIGO and Virgo observatories. When they measure the merger of two stellar mass black holes billions of light-years away, they are detecting a distortion in the fabric of space-time smaller than 1,000th the diameter of a proton. It is the most precise measurement in the history of science, and it opens an entirely new window onto the universe, allowing us to observe cosmic events that produce no light at all. The local group, with its 50-plus galaxies, is bound together by gravity in a way that insulates it somewhat from the broader cosmic expansion. Our fate, The fate of the Milky Way and Andromeda and all their companions is to slowly merge over the next tens of billions of years into a single, large elliptical galaxy. The great spirals will be gone. The star-forming arms will dissolve. But the stars themselves, most of them, will survive, orbiting the new merged galaxy in new paths, in a new configuration, in a universe that by then will look quite different from the one we know. Imagine the universe from far above, not from within, not from any position a human being has ever occupied, but from some impossible vantage point from which the whole can be seen. From this vantage, galaxies appear not as individual objects, but as a pattern, a texture, a structure, and the structure is breathtaking. Galaxies cluster together under gravity. Our local group, the Milky Way, Andromeda, and their companions, is itself falling, slowly, toward a larger concentration of galaxies known as the Virgo cluster. The Virgo cluster sits approximately 65 million light-years from Earth and contains more than 1,300 confirmed galaxies, perhaps as many as 2,000, including the giant elliptical galaxy M87, at the center of which sits the black hole we now have an image of. 65 million light-years. The light reaching your eye tonight from the Virgo cluster left those galaxies 65 million years ago. When the dinosaurs were not yet extinct, when the great asteroid impact that ended the Cretaceous period was recent geological history, those photons have been crossing the void for 65 million years, older than any species alive on Earth today, and they fall, ultimately, into the lens of a telescope or the retina of an eye. The Virgo cluster is massive and dominant. Its gravity reaches out across tens of millions of light years, pulling the local group and many other galaxy groups gradually toward it. We are, in the slow-motion choreography of cosmic gravity, falling toward the Virgo cluster, though we will not arrive there for an almost incomprehensibly long time. The Virgo cluster is part of a still larger structure, the Virgo supercluster, also known as the local supercluster. This is a collection of galaxy clusters and groups extending roughly 100 million light-years in its largest dimension, containing perhaps 100 galaxy groups and clusters and tens of thousands of individual galaxies. 100 million light-years, 100 million years of light travel. But even the Virgo supercluster, enormous as it is, containing tens of thousands of galaxies spanning 100 million light-years, is only a small part of something larger. In 2014, a team of astronomers led by R. Brent Tully of the University of Hawaii mapped the full extent of the cosmic structure within which we reside. They discovered that the Virgo supercluster is not an independent structure at all. It is merely one lobe of a vastly larger supercluster, which they named Laniakea. Laniakea. The name comes from the Hawaiian, meaning immeasurable heaven. It was chosen, beautifully, for exactly the right reason. Laniakea is a supercluster of superclusters. It spans approximately 500 million light-years. It contains roughly 100,000 galaxies, 4 times the number of stars in the Milky Way, expressed now in galaxies instead of stars. Its total mass is estimated at 10 quadrillion solar masses, 1 followed by 16 zeros in solar masses. At the center of Laniakea, at the convergence point toward which all its constituent galaxies are slowly flowing like rivers draining toward a watershed, is a gravitational anomaly called the Great Attractor. It is an enormous concentration of mass hidden behind the dense dust and gas of the Milky Way's disk, which is why it was not discovered until relatively recently. The Great Attractor is pulling our galaxy, our local group, our entire supercluster toward it, and yet The universe's expansion is simultaneously pulling everything apart. These two forces, gravitational collapse and cosmic expansion, compete in a slow, silent tug of war across hundreds of millions of light years. But Laniakea too is not the end. It is not isolated. It is one structure among many, embedded in the largest scale structure of all, the cosmic web. The cosmic web is the large-scale structure of the universe. It is the shape that matter takes on the largest scales, the architecture of everything. Imagine a three-dimensional spiderweb extending to the farthest reaches of the observable universe. Not a regular geometric web, but something organic, complex, filled with nodes where threads intersect and long, curving filaments connecting those nodes. The nodes are galaxy clusters, enormous concentrations of mass. The filaments between them are the cosmic filaments, long, thin streams of galaxies and gas connecting cluster to cluster across hundreds of millions of light years. And between the filaments, between the nodes, between the threads, vast, almost completely empty voids. The voids are staggering. The Bhuta's void, one of the largest known cosmic voids, spans about 330 million light-years. It contains almost nothing, almost no galaxies, almost no gas, almost no ordinary matter of any kind. It is just space. Space on a scale that makes the solar system feel like a crumb on a table, that makes the Milky Way feel like a speck of dust. The cosmic web was not built by anyone. It was not designed. It grew organically from the tiny quantum fluctuations in the first moments of the Big Bang. Improbable variations in density spread across the primordial universe by a period of extraordinary rapid expansion called inflation. Those density variations seeded the growth of structure. Slightly denser regions attracted more matter, grew denser still, eventually collapsed under their own gravity into the first stars and galaxies. Those galaxies clustered together. The clusters assembled into superclusters. The superclusters formed filaments, and the voids between them grew emptier as matter drained away to concentrate in the filaments and nodes. The cosmic web is the record of 13.8 billion years of gravitational storytelling. Every galaxy in every cluster, in every supercluster, in every filament is where it is because of the laws of physics and the initial conditions of the Big Bang, playing out across an incomprehensible expanse of space and time. It is, on reflection, the most beautiful thing I can think of, not designed, not planned, not built by intelligence, just physics, pure impersonal physics, producing something so intricate, so complex, so startlingly structured that it looks, at first glance, like something built. The universe is architecture, and we are the children of one small detail in one small corner of one small filament, looking out at the whole. We have come a long way, from the surface of the Earth to the solar system, from the solar system to the galaxy, from the galaxy to the local group, from the local group to Laniakea, from Laniakea to the cosmic web. Each step has been an expansion of scale so large as to make the previous scale feel almost local by comparison. And now we arrive at the largest scale we can meaningfully discuss: the observable universe. The observable universe is not the same as the universe. It is the portion of the universe from which light has had time to reach us since the Big Bang, because the universe is approximately 13.8 billion years old, and because light travels at a finite speed, there is a maximum distance from which we can have received any information. A cosmic horizon, beyond which lies everything we can never observe, at least not with our current understanding of physics. You might think, given that the universe is 13.8 billion years old, that the edge of the observable universe would be 13.8 billion light-years away. And in a static universe, that would be correct. But our universe is not static. It is expanding, and it has been expanding since the beginning. The space between objects is stretching, and as it stretches, things that were once close have moved far away. The cosmic background radiation, the afterglow of the Big Bang, the oldest light we can detect, was emitted when the universe was only about 380,000 years old. The objects that emitted it were then much closer to us than they are now. By the time that light reached us, 13 billion years had passed, and the universe had expanded enormously. Those objects are now approximately 46 billion light-years away. The observable universe, then, has a radius of approximately 46 billion light-years, making its diameter roughly 93 billion light-years. It is a sphere centered on us, not because we are special, but because we can only receive information that has had time to reach us, which means everything within a certain radius of our position. Any observer anywhere in the universe would see their own observable universe, centered on themselves, extending 46 billion light-years in all directions. Different observers in different parts of the universe see different observable universes with overlapping but non-identical contents. Within this sphere, within the observable universe, there are an estimated 2 trillion galaxies. Not billion, trillion. The most recent estimates, based on deep field observations from the Hubble Space Telescope and analysis of the cosmic structure, suggest that there are roughly 2,000 billion galaxies within the observable universe, most of them too small and too faint to be individually detected. 2 trillion galaxies. If the Milky Way alone contains up to 400 billion stars, then the total number of stars in the observable universe is truly beyond any analogy I could construct. It is somewhere around 10 raised to the power of 24, a septillion in American English. More stars than grains of sand on all the beaches and deserts of the Earth. More stars, in fact, than any intuitive quantity that has meaning to the human mind. Each of those stars might have planets. Many certainly do. The Kepler Space Telescope and other planet-hunting missions have confirmed that planets are enormously common, perhaps the rule rather than the exception. Our galaxy alone may have more than 100 billion planets. Adjust that for 2 trillion galaxies, and the number of worlds in the observable universe is even more staggering than the number of stars. And yet, of all those worlds, we know of only one that harbors life. One world, confirmed. Earth, pale blue, small, beloved. The most distant objects we have ever observed are galaxies in the early universe. Galaxies so far away that their light has been traveling since the universe was only a few 100 million years old. The James Webb Space Telescope, with its extraordinary infrared sensitivity, has now observed galaxies from when the universe was only a few 100 million years old, looking back nearly to the cosmic dawn. The moment when the first stars ignited in the darkness of the early universe, ending the cosmic dark ages. Those galaxies look strange. They are compact, bright, active. The universe was young, star formation was rampant, the metals forged by earlier stellar generations had not yet had time to enrich the gas. They are the ancestors of galaxies like our own, primitive and vigorous, lit by stars that are long dead, whose material has been recycled through generations of stellar life and death to eventually become, in part, the atoms in your body. The light from those distant, early galaxies has been stretched by the expansion of the universe. When it was emitted, it was ultraviolet light. By the time it reaches our telescopes, the expansion of space has redshifted it all the way to the infrared. The expansion of space has quite literally stretched the wavelengths of light as they traveled, turning blue, light, red. This cosmological redshift is one of the key pieces of evidence for the expanding universe. An observational fact that confirms, again and again, that the universe began small and hot and dense and has been growing and cooling ever since. The edge of the observable universe is not a wall. There is no wall. Beyond the edge of what we can see, the universe almost certainly continues. Perhaps for a very long time, perhaps indefinitely, perhaps forever. We simply cannot know because no light from beyond that horizon has had time to reach us. The universe beyond our horizon may be essentially identical to what we see within it. More galaxies, more stars, more worlds. Or it may be different in ways we cannot predict. Some theories of inflation suggest that the universe is unimaginably larger than the observable portion, perhaps infinite. And at the very edge of the observable universe, there is one more thing to contemplate: the cosmic microwave background. The CMB is the oldest light in the universe. It is the thermal radiation left over from when the universe, 380,000 years after the Big Bang, cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. Before that moment, the universe was opaque. Light couldn't travel far before being absorbed and re-emitted. When the universe became transparent, that last scattered light flew free in all directions, and it has been traveling ever since. Today, it fills the entire observable universe uniformly, diluted and cooled by billions of years of cosmic expansion, from thousands of degrees to just 2.725 degrees, above absolute zero, nearly 3 degrees above the coldest possible temperature. You can almost detect it yourself. A fraction of the static in an analog television tuned to an empty channel, that hissing, flickering snow, is the fingerprint of the Big Bang, left in the form of microwave radiation reaching your antenna from every direction in the sky simultaneously. You were, in a very loose sense, watching the Big Bang. The CMB is nearly perfectly uniform, but nearly is the key word. There are tiny, exquisitely small fluctuations in temperature across the sky. Variations of about 1 part in 100,000. These tiny ripples are the seeds of all structure in the universe. The fingerprints of the quantum fluctuations in the infant universe that eventually grew, under gravity, into the galaxies and clusters and filaments we see today. The universe wrote its autobiography in the CMB, and we have learned to read it. The observable universe is 93 billion light-years across. It contains 2 trillion galaxies. It is 13.8 billion years old. And in all of it, in all that time and space, in all those galaxies and stars and worlds, we have found one place so far that holds what we hold: life, consciousness, wonder. Just one, just here. The James Webb Space Telescope, launched on Christmas Day 2021, has fundamentally transformed what we can see of the early universe. Its golden mirrors, cooled to nearly absolute zero, collect infrared light from distances so great that the objects emitting it are seen as they were when the universe was only a few 100 million years old. The images it has sent back are almost indescribably beautiful. Galaxies that look like jewels on black velvet, gravitational lensing arcs where massive galaxy clusters bend and magnify the light of more distant objects into brilliant streaks and arcs, stellar nurseries where new stars are being born in towering columns of gas and dust, sculpted by stellar winds and radiation. The pillars of creation, the famous image originally captured by Hubble in 1995, was re-imaged by JWST in infrared, revealing not just the majestic columns of gas and dust, but the previously hidden stars inside them, young stellar objects caught in the act of formation. The image shows something happening right now. Well, right now meaning 6,000 years ago when the light left. In the Eagle Nebula in our own galaxy, a relatively modest distance away. What JWST can show us from far greater distances is the universe at its dawn. The first galaxies forming in the first few 100 million years after the Big Bang are now being studied in detail. They are small, dense, irregular, nothing like the grand spirals we know from the modern universe. They are the seeds from which all the structure we see today eventually grew. Some of these early galaxies appear to be more massive than models predicted they should be at such early times. A possible tension between observation and theory that has generated considerable discussion in the astronomical community. Whether this represents a fundamental challenge to the standard cosmological model, or simply a refinement of our understanding of early galaxy formation, is still being worked out. This is what science looks like from the inside. Observations, models, tensions, revisions, deepening understanding. The Hubble Deep Field, the famous long exposure image from 1995, showing nearly 3,000 galaxies in a patch of sky no larger than a grain of sand held at arm's length, was the first glimpse of just how many galaxies the universe contains. Each smudge of light in that image is a galaxy. Each galaxy contains billions of stars, and that tiny patch of sky represents a tiny sample of the 360 degrees of sky surrounding Earth. Scale that up. Apply that density of galaxies to the entire sky, and you arrive at the estimate of 2 trillion galaxies in the observable universe. 2 trillion islands of stars, each containing hundreds of billions of suns, each potentially harboring billions of worlds. The Hubble Ultra Deep Field, the Hubble Extreme Deep Field, and now JWST's deep fields have each pushed further, shown us more. Each one has confirmed again and again the astonishing abundance of galaxies in the universe. The night sky, if human eyes could see in all wavelengths with arbitrary sensitivity, would be blazing with the light of those 2 trillion galaxies. As bright as a full moon in every direction, the sky would be a sea of light. Instead, it appears dark at night. This is a puzzle that was first clearly articulated by the German astronomer Heinrich Olbers in the 19th century and is known as Olbers' paradox. If the universe is infinite and static and filled with stars, why is the night sky dark? The answer, we now know, is twofold. The universe is not infinite in observable extent, and it is not static. It is expanding. The expansion redshifts the light of distant galaxies beyond the visible spectrum. And because the universe has a finite age, the light from the most distant galaxies has not yet had time to reach us. The sky is dark because the universe is young and expanding. Its darkness is evidence of its history. In 1 trillion years, when the accelerating expansion has carried most galaxies beyond our observable horizon, when all the stars in our galaxy have burned out or dimmed to red dwarfs, when the darkness is deeper than we can imagine, any beings that exist will look out at a sky that shows almost nothing beyond their own galaxy. They will be cosmological islanders, unable to see any evidence that other galaxies ever existed. They will have no way of knowing what we know, that the universe was once teeming with 2 trillion brilliant galactic cities. We live at a fortunate time to be doing cosmology. We have traveled far. We have moved from the familiar surface of the Earth to the edge of the observable universe. From the scale of footsteps to the scale of 93 billion light years. We have passed through the solar system, crossed interstellar space, visited the arms of our galaxy and the heart of our supercluster, traced the filaments of the cosmic web, and stared into the microwave afterglow of creation itself. And now, at the edge of what we can observe, we stand at the edge of something else, what we can understand. Because science, for all its astonishing power, has limits, not failures, limits. There is a distinction. The limits of science are not places where knowledge has broken down. They are places where knowledge has brought us right to the edge of what is currently knowable and then pointed, honestly, at the fog beyond. Let us sit with some of that fog. Matter, as we noted earlier, accounts for roughly 27% of the total energy content of the universe. Ordinary matter, the stuff of atoms, of stars, of galaxies, of you, accounts for only about 5%. The remaining 68% is something called dark energy. Dark energy. In 1998, two independent teams of astronomers were measuring the distances and recession velocities of Type 1a supernovae. Stellar explosions so bright and so consistent in their luminosity that they serve as reliable, standard candles for measuring cosmic distances. What they found, and what earned three of them the Nobel Prize in Physics in 2011, was shocking. The expansion of the universe is not slowing down. It is accelerating. The universe is expanding faster and faster with time. In the standard cosmological model, the Big Bang set the universe expanding, and gravity, the attractive force between all matter, should be slowing that expansion down over time. It should be decelerating. Instead, it is speeding up. Something is pushing the universe apart, driving the expansion faster and faster. That something is dark energy. It fills all of space uniformly. It does not dilute as the universe expands. Unlike ordinary matter, which spreads thinner as the volume grows, dark energy maintains a constant density. It is not a substance in the normal sense. It may be a property of space-time itself. What Einstein called the cosmological constant, a term he introduced to his equations of general relativity in 1917 to model a static universe, ironically, and then famously called the greatest blunder of his life when Hubble discovered the universe was expanding. Then, decades after his death, the cosmological constant turned out to be real after all. We do not know what dark energy is. We know what it does. It drives the accelerating expansion of the universe. But we do not know its nature. We cannot measure it directly. We cannot bottle it, study it, manipulate it. We can only infer its existence from its effects on the large-scale motion of the universe. Dark matter is similarly mysterious. We know it exists from its gravitational effects. We know where it is, or roughly where it is, from the way it bends light through gravitational lensing, from the motion of galaxies within clusters, from the patterns of the cosmic web. We know how much of it there is, but we do not know what it is made of. Physicists have proposed numerous candidates: weakly interacting massive particles, WIMPs, axions, sterile neutrinos, primordial black holes. Many experiments have been designed to detect dark matter particles directly. So far, none has succeeded. In summary, 95% of the universe is made of things we cannot directly detect. We can observe the universe, map its structure, trace the history of its expansion, and 95% of everything in it remains fundamentally mysterious. There is something both humbling and exhilarating about this. Humbling, because it reminds us that our picture of reality is, at best, partial. Exhilarating because it means that the greatest scientific discoveries in human history may still lie ahead. We are not at the end of science. We are at the beginning of understanding. What lies beyond the observable universe? Honestly, we don't know. The universe may be finite, curved back on itself like the surface of a sphere, so that, in principle, you could travel in any direction and eventually return to your starting point. Or it may be infinite, extending without bound in all directions. Current evidence suggests the universe is very large, possibly infinite, but we cannot confirm this with present technology. There are theories, and they are theories, not confirmed science, that suggest our universe may be one of many. The multiverse. Versions of this idea appear in different theoretical contexts. In string theory's landscape of possible physical constants, in the eternal inflation model's endlessly inflating quantum foam, in the many worlds interpretation of quantum mechanics. The multiverse is not a fringe idea. It is taken seriously by serious physicists, but it is also not confirmed science. We do not yet have any way to observe other universes or even to confirm that they exist. What caused the Big Bang? This is perhaps the deepest question in all of science. General relativity breaks down at the singularity, the initial moment of infinite density and temperature. Our equations simply do not work there. A quantum theory of gravity, something that could reconcile quantum mechanics and general relativity, might one day give us a description of the very beginning. String theory, loop quantum gravity, and other approaches have been proposed. None has yet succeeded in producing a complete, testable theory. We might be approaching, slowly, haltingly, across generations of scientific work, answers to some of these questions. Or we might discover that the questions themselves were incorrectly posed. The history of science is full of moments when the right answer turned out to require a completely different way of asking the question. And then there is perhaps the deepest mystery of all: consciousness. Why is there something it is like to be a human being? Why does the universe know itself, not just in the metaphorical sense of galaxies and stars and planets, but in the literal, first-person, subjective sense? Why is there experience? Why is there an inside to being a mind? The universe has no obvious reason to know itself. Physics does not require consciousness. The laws of nature can, in principle, operate entirely without any observer, without any inner life, without any awareness whatsoever. And yet, here we are, aware, experiencing, looking out at all of this and feeling something about it. If the universe is 13.8 billion years old, and the Earth formed 4.6 billion years ago, and life appeared perhaps 4 billion years ago, and multicellular life only 600 million years ago, and conscious life only a few million years ago, and reflective human consciousness only a few 100,000 years ago. Then the universe has been going about its business, its stars burning and its galaxies colliding and its voids emptying, for the vast majority of its existence without anyone watching. And then, in the last cosmological eye blink, something began to watch. You are the universe watching itself. The atoms in your body were forged in the hearts of stars that died billions of years ago. The carbon in your cells, the oxygen in your lungs, the calcium in your bones. They are stellar debris, recycled through the interstellar medium and incorporated into you by the vast, impersonal processes of chemistry and biology over billions of years. You are, in the most literal sense, made of stars. And now those atoms, organized by the remarkable accident of evolution into something capable of thought and feeling and wonder, are turned back on the cosmos that made them, trying to understand it. That is what science is, not merely the accumulation of facts, not merely the engineering of better technology. It is the cosmos developing the ability to understand itself through the medium of minds that are themselves part of the cosmos. The mystery does not diminish the wonder, it deepens it. The questions we cannot answer are not failures. They are invitations. They are the places where the next generation of scientists will make their mark. Where some young mind, perhaps alive right now, perhaps too young to read these words, will one day have an insight that opens a new door in human understanding. What is dark matter? What is dark energy? What lies beyond the observable universe? What came before the Big Bang? How did life begin? Are we alone? These are not embarrassments for science. They are its most precious possessions, the open frontiers, the uncharted territories, the places where curiosity can roam freely, where discovery is still possible, where the universe has not yet been translated into language. Sit with the not knowing for a moment. It is not uncomfortable if you approach it correctly. It is one of the most human things there is. To look at the immensity and mystery of the cosmos and say, I do not understand, but I want to. That wanting, that reaching, that is what has brought us this far. One of the deepest puzzles in modern cosmology is the nature of the Big Bang itself. The standard cosmological model, the lambda CDM model, where lambda represents the cosmological constant, dark energy, and CDM stands for cold, dark matter, describes the universe from about 1 second after the Big Bang with remarkable accuracy. It predicts the abundances of light elements produced in the first few minutes of nucleosynthesis. It predicts the structure of the cosmic microwave background. It predicts the large-scale structure of the universe. It is by any measure one of the most successful physical theories ever formulated. But it says nothing about what came before the Big Bang, or what caused it, or why the initial conditions were what they were. General relativity, the theory of gravity that underlies the cosmological model, breaks down at the singularity, that initial state of infinite density and temperature. Something else is needed to describe that moment, if moment is even the right word for it. The theory of inflation, the idea that the very early universe underwent a period of extraordinarily rapid expansion, doubling in size many times in a tiny fraction of a second, was proposed in the 1980s by Alan Guth and others to solve several puzzles in standard cosmology. Why the universe is so flat, why the CMB is so uniform, why there are no magnetic monopoles. Inflation has been spectacularly successful at addressing these puzzles, and some of its predictions have been confirmed by observations of the CMB. But it raises new questions. What drove inflation? What ended it? And the mechanism of eternal inflation, which the mathematics of inflation models seems to require, suggests that inflation never fully stops, that bubble universes are continually nucleating out of an eternally inflating background, each with potentially different physical constants. This is the multiverse, not a single universe, but an infinite, self-generating foam of universes, each sealed off from the others by the causal structure of space-time, each perhaps with different physical constants, different particle masses, different strengths of forces. In a multiverse of this kind, the question, why does our universe have the laws it does, acquires a different flavor. We observe a universe with laws compatible with the existence of stars, planets, and life, because only in such a universe could observers evolve to ask the question. This is the anthropic principle, not a physical explanation in the traditional sense, but a selection effect. We are here because the laws of our universe permit us to be here. That is a logically valid observation. Whether it is a satisfying explanation is a matter of ongoing philosophical debate. There is something both wondrous and unsettling about the multiverse. Wondrous because it suggests that the cosmos is even larger, even more complex, even more astonishing than the observable universe alone. unsettling because if other universes exist but are causally disconnected from ours, we can never observe them, never confirm their existence by any direct measurement. A theory that cannot, even in principle, be tested is on shaky epistemological ground. The boundaries between established science, well-motivated speculation, and philosophy are not always clearly drawn in this territory. That is not a criticism, it is simply a reflection of the fact that we are pushing at the very limits of what current science can address. The questions are real and important. The answers, if they come, will require new mathematics, new observations, new ways of thinking about reality. This is the frontier. And frontiers, by definition, are places where the familiar ends and the unknown begins. There is also the question of time itself. We speak casually of before the Big Bang, but time, according to general relativity, is a dimension of space-time, not a backdrop against which events unfold. If space-time itself began with the Big Bang, then there was no before. Asking what came before the Big Bang is like asking what is north of the North Pole. The question may simply be malformed, or it may require a new conception of time to answer properly. Stephen Hawking, with James Hartle, proposed the no-boundary model of the universe. The idea that at very early times the distinction between space and time becomes blurred, and that the universe has no boundary in time, no initial moment, no singularity. In this model, asking what came before the Big Bang is similarly meaningless. There is no before in the same sense that there is no before to the surface of a sphere. These are deep waters. The honest answer for now is, we don't know. And that is perfectly fine. It is, in fact, scientifically exciting, because the uncertainty means there are discoveries still to be made, insights still to be won. The universe has not finished surprising us. We have been gone a long time in imagination, if not in time. We have traveled through scales that defeat language, through distances that defeat any number that feels real, through ages that make human history feel like a brief, bright flash. But now, let us come back. Let us fall back through the scales, back through the superclusters and the galaxy clusters, back through the Milky Way and the solar system, back through the silence of interstellar space and the cold darkness of the Oort cloud, back through the orbits of the outer planets and the bright fury of the inner solar system, back past the moon, back through the blue atmosphere, back to the ground, back to you, here, now. Sit for a moment with what you've seen. You began this journey standing on the surface of a planet 12,742 kilometers across, a world that felt large, that feels large, that in the context of everyday life is overwhelmingly large. And you have just seen that this planet, this enormous world, this ocean-covered globe, that is the entirety of everything most human beings have ever known and touched and loved, is invisible on a map of the universe. Not small, not insignificant, invisible, too small to show up, too small to indicate with an arrow, a speck among specks among specks among specks. The observable universe contains 2 trillion galaxies. The Milky Way alone contains perhaps 250 billion stars. Our Sun is one of them, an average, unexceptional, yellow dwarf star in a quiet suburb of a spiral arm. And around it, at a distance of 1 astronomical unit, orbits a small rocky planet with a thin, fragile atmosphere and a thin, fragile biosphere, and a species of upright apes with large brains and small hearts, gazing outward with instruments they have built from the materials of the Earth, trying to understand where they are. If you compressed the entire history of the universe into a single year, the cosmic calendar, as Carl Sagan famously described it, Then the Big Bang happens at midnight on January 1st. The Milky Way forms in March. The solar system forms in early September. Earth forms mid-September. Life appears by late September. Multicellular life doesn't arrive until mid-December. The dinosaurs go extinct on the 30th of December. All of recorded human history, every civilization, every war, every discovery, every poem, every song, happens in the last 10 seconds before midnight on New Year's Eve. 10 seconds. In the cosmic calendar, the whole of human civilization is less than 1 minute of the year. The entirety of what we know, have built, have loved, is a few grains of sand from the beach of time. And yet, there is something about those 10 seconds that the previous 31,535,990 seconds entirely lacked. There is something about this particular speck of rock, in this particular quiet corner of this particular galaxy, that the 2 trillion others, so far as we know, do not have. There is something it is like to be here. There are beings here who know that they exist, who know that they will die, who know that the stars are far away and that the universe is old and that time passes without mercy, who write music to describe what they feel when the light is right, who build telescopes to see beyond their own eyes, who ask questions that have no answers yet and refuse to stop asking. There are beings here who are afraid of the dark and who look at the darkness anyway and find in it, slowly, patiently, generation by generation, something like light. The Earth is a miracle, not in any supernatural sense, but in the most precise scientific one. The probability of what has happened here on this small world, in this particular arrangement of chemistry and circumstance and time, is so extraordinary, so contingent on so many improbable coincidences, that the word miracle seems, for once, like the right word. The sun burns at exactly the right temperature. It is the right type of star, and not too massive, not too small, stable enough to burn steadily for 10 billion years, giving life time to develop and flourish. The Earth orbits at exactly the right distance. In the habitable zone, where water can be liquid on the surface. The Earth has a magnetic field generated by its liquid iron core, which deflects the solar wind and protects the atmosphere from being slowly stripped away, as happened to Mars. The Moon is unusually large relative to the Earth, stabilizing our axial tilt and moderating the seasons. Jupiter, out in the outer solar system, acts as a gravitational shield, intercepting many comets and asteroids that might otherwise strike the Earth with devastating frequency. One thing different, one variable off, and perhaps none of this happens. Perhaps the Earth is sterile like Venus. Perhaps it is frozen like the outer moons. Perhaps the great chain of coincidences that led from hot rock to ocean to prokaryote to fish to fern to dinosaur to mammal to you was never initiated. But it was. Here on this one world, the chain was initiated. And it ran. 4 billion years of life. 4 billion years of organisms struggling, adapting, dying, evolving. Each generation passing the gift of existence forward in an unbroken chain. From the very first cell to every living thing breathing and growing and singing on this planet right now. You are the product of an unbroken chain of survival 4 billion years long. Every single one of your ancestors, going back to the very beginning of life on Earth, managed to survive long enough to reproduce. Not one of them failed to pass on the gift of existence. They lived, and they loved, and they struggled, and they passed on what they had. And eventually, across billions of generations and billions of years, they produced you. That is not nothing. In the context of a universe that is overwhelmingly cold and dark and empty and impersonal, that is everything. Carl Sagan, perhaps the greatest science communicator of the 20th century and one of the wisest voices ever to speak about humanity's place in the cosmos, wrote these words in his description of the pale blue dot. The famous photograph of Earth taken by Voyager 1 in 1990, from a distance of 6 billion kilometers, in which Earth appears as a tiny point of light, less than a pixel wide in the vastness of space. Look again at that dot. That's here, that's home, that's us. He went on to describe what is visible in that image, all of human history, all of human achievement, all of human suffering and joy and love and hatred on that tiny mote of dust suspended in a sunbeam. And he drew from it not despair, but a kind of moral clarity. If this is all we have, if this one small world is the only home we know, then perhaps we should take better care of it and of each other. That thought, that quiet, serious, cosmically grounded moral thought, is one of the most important things astronomy has ever given us. Not just knowledge of distances and temperatures and the age of the universe, but perspective. The kind of perspective that makes the things that divide us seem small and the things that connect us seem enormous. We are here together, on one small world, in a corner of one galaxy. In a universe of 2 trillion galaxies stretching across 93 billion light-years, filled with mystery and beauty and dark matter, and dark energy and quantum foam and ancient light and the frozen echoes of the Big Bang. And in all of that, in all that immensity, we have only ever found life here. That should make this world sacred to us. Not in a religious sense necessarily, though if it inspires something like reverence, that seems appropriate. Sacred in the sense of being precious beyond price. Sacred in the sense of being worth protecting, worth treating with care, worth handing on intact to those who come after us. We look outward and find vastness. We look inward, back to the small blue world, and find meaning. These two things are not in conflict. They are, in fact, the same thing, seen from different angles. The vastness of the universe is not a statement about our insignificance. It is a statement about the scale of what we are embedded in, the context of which we are a part. We did not choose this context. We inherited it, along with our atoms and our DNA and our capacity for wonder. And we have done something remarkable with it. We have looked out with our naked eyes, with telescopes of increasing sophistication, with space probes and radio dishes and gravitational wave detectors and neutrino observatories. And we have seen. We have understood. Not everything, not even most things, but something real and deep and true. We know the universe is 13.8 billion years old. We know it began in a state of extraordinary heat and density and has been expanding and cooling ever since. We know it is made of quarks and leptons and force-carrying bosons, organized by 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Into the complex structures we observe. We know it contains dark matter and dark energy, though we cannot yet say what they are. We know it is full of galaxies and stars and planets, and that those planets are common, and that the chemistry of life is widespread, and that here, on at least one world, that chemistry woke up and asked a question about itself. We know all of this because of curiosity, because of the willingness to ask why and how and when and where, because of the stubborn, irrepressible human impulse to understand. Curiosity is the most cosmic thing about us. In a universe that doesn't care, doesn't notice, doesn't ask questions, curiosity is our response. It is the way we reach back toward the cosmos that made us, trying to understand it as it cannot understand itself. Look up tonight. If the sky is clear and you can find a dark place, look up. Find the Milky Way if you can, that ghostly band of light arching across the sky. Look for Andromeda, that faint smudge if you know where to look. The nearest large galaxy, 2.5 million light-years away, visible to the naked human eye. Look at the stars and remember that their light is old, that some of them have died since that light began its journey, that you are receiving messages from the past with every photon that enters your eye. And then look down, at your hands, at the ground, at the remarkable, improbable, 4 billion-year-old world that made you and holds you and breathes for you. You are small. The universe is large. Both of these things are true. Both of these things are beautiful. From this small world, we look outward. And in looking, we find something no telescope can directly show us. We find that the universe, in having made something capable of wonder, has given itself the gift of its own witness. The universe is looking at itself through your eyes. The universe wonders about itself through your mind. Whatever else you are, whatever else you do, whatever you achieve or fail to achieve in the brief and luminous time you have here, you are part of this. You are a part of a 13.8 billion year story that began in a fireball and produced, among other things, galaxies and stars and worlds, and on one small world, the capacity for love and loss and music and mathematics and the overwhelming, quiet, persistent, inexhaustible human need to understand. That is enough. That is more than enough. That is everything. We are infinite science. Thank you for watching and for wondering. The cosmos awaits.